Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, everybody. Hello, everybody. My name is Paul Oka. I'm kicking off this session from Randy Davis and Kimberly Collet, who are researchers I'm working with at MIT through the iCampus program. And they're doing very interesting research on sketch recognition. And Kimberly's actually working with the Conference XP team and a presenter from UW. With that, I'd like to introduce Randy.
Thank you. The problem we're really interested in is the notion of natural interaction. So what's natural interaction? My favorite example to use is this sketch of a conceptual design for a circuit breaker. The basic idea is I've got a piece of metal hanging down here, which is free to swing. There's a spring, which is tending to push it counterclockwise. There's this piece of metal here, which is a bimetallic strip. There's a wire connected here, a wire connected here. And the basic idea is if too much current flows through here, this will heat up, it'll bend down, opening up the circuit, and now my circuit's broken. Understand? Okay, that's amazing. I mean, heads are nodding, and all I did was show you a really crude pencil sketch, wave my hands literally around it a few times, say about 100 words, and yet some number of you said, yes, you understand. Well, that's what I want my computer to do. I want to be able to walk up to a surface on which I can draw, gesture, and talk. And when I draw something like this and talk about it this way, I want the machine to say I understand, and what it means by that is what I think you meant by that. So what does it mean to say you understand? Well, part of it is you can kind of imagine a movie in your head of this thing behaving. Another part of understanding is to tell me, let's see, what is this supposed to do? This is a little wall, a stable wall. This is something I can push, and that's a spring holding that out that way. So if I push on this, why is that there? It's one possibility is a manual brake. What else could it be? It's a reset button. Okay, so what it means to understand is, among other things, to be able to tell me the intended behavior of things that I never even mentioned in the explanation. Okay? So this is what I want to do. I want to be able to describe, draw, and gesture at things and have the surface that I'm working with be smart enough to understand what I'm doing and to exhibit the kind of behavior we're talking about here. Here, more generally, is what we're after, the notion that designers can work in a fashion that feels natural to them. Instead of sitting at a keyboard, they can sit at some sort of sketching environment, and I'll talk about that a little later on, sketching with what feels like pencil and paper, and have the sense that there is embedded in the environment with them, either literally or figuratively, something that's looking over their shoulder and, for the most part, understanding what they're doing without having to ask. But, of course, even if that was literally a human being standing there, they wouldn't always understand everything that's going on, so they occasionally have to ask questions of the designer. But if those questions can be asked out loud and the answer can be given out loud, and in fact, I think that would be unobtrusive enough that somebody might actually like to work in that kind of environment. Because after all, designers often like to talk about what they're doing. They don't want to write documentation, but they don't mind intelligent questions. So the key is to make the observer intelligent enough that the questions are reasonable ones. Now, we started this looking at sketches in particular because, of course, sketches are ubiquitous in lots of design and other kinds of tasks. Here's the circuit breaker I was talking about before. Here's a sketch of the architecture for an object-oriented program, some class structures. Here's the kind of problem that probably drove you crazy in undergraduate physics courses. And here's a real sketch of a tennis ball tosser that I found on the web. It's a conceptual design for something that sits at the other end of the court and tosses tennis balls at you so you can practice. So the good news is all of us think in terms of drawing all the time. The bad news is, given our current technology, sketches are for the most part dead. They are carboned on dead trees or even with the devices sitting in front of you, for the most part, they are electronic ink, which has been captured. But I want to do more than capture the ink. I want the ink to be understood. So we created this system that goes by various names. The general name is Magic Paper, which kind of sets our aspiration. We'd like something that feels as natural as paper to work with, and yet is a whole lot smarter than that. And as was mentioned in one of the earlier sessions today, the first instantiation of this is a system that works on simple two-dimensional physics problems, where you can sketch out an example and see the system that you've sketched out actually behave. Now, in order to show you that, I've got an example set up here on a tablet PC that's right in front of me. As you can see, this is indulging the 6-year-old in me. All of you can tell what's going to happen, right? Let me just tell you a few things about notation. This is an arrow meaning gravity. Whoops, where is it? This is an arrow that means gravity. Here's my pendulum. X means anchored to the background. Okay, and keep in mind this is two-dimensional physics. Notice the run button up here. If I asked you what was going to happen next, you know perfectly well what would happen. What I want is the system to understand what's going to happen. And there it is, animated. Now, just to show you this isn't just a one-trick pony just for fun, I'll put a little board here, anchor it to the background, and then we'll try putting a spring here. Okay, now let's try this again. Okay, it doesn't work as well. Okay, so the point is, what you can draw with a vocabulary of simple physical components that we've created, our system can understand. And the idea is to be able to interpret that, make sense of it, and animate it in real time as a way of understanding designs, understanding physics. We see a number of different applications possible here. Here's a slightly more complicated example that I drew once before. It takes a while to draw, so I won't do it in real time. Just to give you the idea of the icons, circles that are tangent are interpreted as a gear train. That's the symbol for a motor. Here's a pulley system. Here's a rod with a coil spring around it, connected with a pin joint to this piece of metal. These three things are anchored to the background. The basic idea is it's a parts feeder. The parts drop down here. This is supposed to move back and forth, pushing them out one by one. This is the raw example, the raw strokes. Here's the cleaned up strokes. And then here's the system in action. Here's the system in action. Cue the action. For some reason, it doesn't want to. Okay, take my word for it. It works reasonably well. Say again? Yeah, sure. It's supposed to work anytime I touch anywhere on it. Who knows? All right. One of the long-term themes of this work is that natural interaction is knowledge-based. You guys are sitting there listening to me talk, watching me gesture, and even watching me draw, and you're understanding what I'm doing. And if you ask, how is it that you manage to understand, I think you'll find that the answer is you know a lot. You know a lot about the language that I'm using, the grammar that I'm using, what speech sounds like, what gestures mean, the domain that I'm talking about, two-dimensional physics. And we think what's true of people is going to have to be true of programs as well. If it's going to be easy to interact with the system, it's got to be, I think, because that system has to be reasonably smart. So one of the underlying themes of our work is to try and take advantage of as much knowledge as we can from different sources to try and make the system smart so that it's easy to interact with. Here's a rough idea of the architecture that we've got. Our earliest architecture was a simple blackboard system. Did some early processing, basically looking for corners and curves and such. And we wrote a bunch of hand-coded recognizers. So each of the symbols in that parts feeder example, for instance, was recognized by an individual Java routine that tried to find it on what the user had sketched. Before very long, we decided that was just way too time-consuming, and it was going to be hard to come up with recognizers for other domains if we had to write Java code all the time, and it would be difficult for other people to do. So we said, wouldn't it be much nicer if instead of having to write a piece of code, you could instead say, look, this is the symbol I would like to recognize for a new domain. And you know what that looks like? That looks like this. I'd like to be able to describe that symbol by saying, look, here are the parts. It's got 3 lines and an arc. Here are the relationships among the parts. And now I've described that shape. Wouldn't it be nice if I could describe the shape instead of having to write Java recognizers and have the system work off this description to do its recognition? Okay, well, that's pretty good, except who wants to type descriptions of shape? I mean, I said we're interested in natural interaction, right? Typing is not a particularly natural way to describe shape. So instead, what we'd really rather do is be able to draw this, have the system figure out that, well, let's see, that's really 3 lines and an arc in a certain relationship, and then have it generate that description. And in fact, we've done some work on this. The basic idea is, let me back up for a sec. The hard part is telling what's important about this. The good thing about a sketch is it has a lot of information in it. The bad thing is it has a lot of information in it. In particular, these lines have a precise length and a precise angle between them. Yet you don't attend to that. You attend to the fact that these look like parallel lines of roughly the same length. That is, your perceptual system does a certain kind of preferential generalizing. It turns out that some experiments in the 1930s helped to identify the kind of things that your eye and brain attend to. Here's an example. If I asked you to describe that line, what would you say? This is not a deep question. It's a straight line. What else? Slanted. Okay, so it's a slanted line. Describe that line, please. Vertical. Okay, that's interesting. What have I got here? What do I have there? Ooh, okay. So it turns out your eye and brain attend that's the word I'm looking for. Have a preference for attending to certain sorts of configurations. So we see things like verticality or horizontality. We see things like parallelism. And these things were called singularities because, well, consider, if I take this and tilt it a little bit, it's still a slanted line. If I take this and tilt it a little bit, it's no longer a vertical line. The property is delicate. It's fragile. Same thing with the parallelism. Tilt that line a little bit, they're no longer parallel. So our eyes and brains tend to attend to these things that seem not to be accidental, that seem not to happen by chance. And so our system does the same thing. It looks at the hand drawing and says, what are the things that might be the singularities in there that I ought to attend to? And it generates a description of the shape. So more generally, what we have is a language for shape and drawing sequence description. Notice it's not just shape, it's the sequence in which you draw the thing, because we're drawing on a tablet and the timing of each stroke is available as well. So we want to be able to go from one example, taking the shape and sequence description language, learning that icon, producing a symbolic description, then turning that symbolic description into code so that we have new recognizers. This is the aspiration that we're making some reasonable progress on. And by the way, I said we wanted all this to be multimodal as well, and I'll illustrate how we're working on that too. So the general notion is to have a system like this, whose fundamental job is to turn pixels into objects. You draw on the screen. Its job is to interpret the things you drew, turn them into descriptions of objects, and then hand that off to a back-end application. The animation that you saw of the physical device that was running on my tablet here is an off-the-shelf Newtonian simulator. Our job isn't to do the physics. Our job is to understand what it is that was sketched on the screen. So more generally, what we're talking about is sketch-enabled and eventually gesture and speech-enabled interaction, where we're not particularly concerned with the application. Our idea is to figure out what you drew, and we'll hand it off to most anything on the back end, be it a simulator, a design checker, a design critiquer, anything like that. Now, I also said we're interested in multimodal interaction. Here's a toy that many of you have probably seen, right? Fun to play with. Early on in building our 2D physics simulators, somebody said, hey, that's cute. Why don't you draw that? Do you know how hard it is to draw this thing? You know why? In order to have it work, you have to draw 3 pendulums that are identical in size and just touching. Do you know how hard it is to draw 3 identical pendulums that are just touching? Did you notice how easy it was to say that? So why am I struggling to draw what's easy to say? Why not think a little bit carefully about graphical and verbal communication and think not just that I want to use both of these things, but what's the appropriate kind of communication to be expressed in each modality? And in order to show you the kinds of things we've done with this, here's a quick demo of one of my students, combining speech and sketching. That's the equivalent of an electronic whiteboard he's drawing on. He doesn't really have a marker in his hand.
There are 3 identical touching pendulums.
Okay, so the idea is you draw what's easy to draw, say what's easy to say, and the two of those ought to work together to make it much easier to describe the devices that you're trying to describe. Now, I also said we want to be able to understand gestures. So the interesting issue here is understanding the vocabulary of gestures, because it turns out not a whole lot is understood about how people use their hands. So the first question we have to ask is, how do people gesture? Well, it turns out it depends on the task. If you and I are having a face-to-face conversation, I make one kind of gesture. If I'm up here lecturing at you, I make another kind of gesture. So we ran a simple user study in which we asked people to explain how something worked. We showed them a simple movie like this, an animation. Okay, refuses to work. It's a little pendulum, a piston, and it moves back and forth. So we showed them an animation like that, and then stood them in front of a whiteboard with a drawing like that and said, explain to us how it works. We videotaped people and attended to every gesture they made, every hand movement, and tried to analyze it. One of the things we discovered is, not terribly surprisingly, almost all the gestures referred to the diagram, people pointing here. An awful lot of them were two-handed gestures, which are much more common here than they are in other kinds of tasks. And finally, the deictic gestures, pointing things, this, that. Those kinds of gestures are much more common in this kind of task than in other kinds of interaction. And this is the beginning of helping us to understand, if you will, the lexicon and grammar of gestures. What do people do with their hands, and how do they use them? Now, how many people here know about Wizard of Oz experiments? Okay, it would be worth it to say a word or two. We'd really like to have a tablet or other environment where you could draw and talk. And we want to build a system that makes it easy for people to interact with something like that the way they would interact with it. The problem is, in order to know how they'd interact with it, we need one that works. Okay, so the trick is what's called the Wizard of Oz experiment, where you build software that allows you to simulate it out of the sight of the person who's actually using it, so they can draw and talk to a tablet, and they have the experience of a tablet that understands both their drawing and their talking. So we've spent a fair amount of time developing software that allows us to have a user draw on one tablet and have that information show up on a central system, and allowing the person in the central system to draw back again on the tablet, giving the person the experience that this is a system that really understands him. All of that, in turn, so we can run user studies to see how people would actually behave if they had an environment in which they could draw and talk and be understood. Now, let me go back to the question of sketch understanding in particular and look at that in a little bit more detail. We wanted people to sketch in a way that felt completely natural to them, so we had to give them something to draw that they wouldn't have to think very hard about. The idea we came up with was to ask them to draw their family tree, because everybody's got a family. So we gave them a simple vocabulary, a graphical vocabulary, and said, draw your family tree for us using this graphical vocabulary. This is the kind of thing we wound up with. Here's a real example from one of the sketches people drew. The numbers are the order in which the strokes appeared. And this is interesting in part because it gives you just a hint of some of the difficulties in trying to do sketch understanding. First of all, the task is incremental. That drawing isn't finished yet, but we want to understand it even as it's being drawn in order to keep up with the complexity of making sense of it, and also, in case the system is making a mistake, to give feedback to the user so that they know that they can indicate something's going wrong. Second, the signal's noisy. This is, of course, supposed to be a rectangle, but it sure doesn't look much like one. Styles vary. Notice that this rectangle was drawn with a single stroke. This one with a U-shaped facing left and then a stroke there. This one with two L-shaped, 6 and 7. So even though it's a rectangle, it's been drawn in several different ways, even within the same diagram. This is why it's difficult to use the kind of techniques that, for instance, Palm's graffiti tries to use, where there are established ways to draw things in order to make the recognition task easier. Segmentation is difficult. Consider stroke 12. What does it belong to? Well, it clearly overlaps this thing, so you might be tempted to say these two go together. But of course, you're looking at this and making sense of it in a different way and understanding that it probably belongs with stroke 8. And finally, this stuff is not only two-dimensional, it's also non-chronological. What do I mean by that? Consider 8, 9, 10, and then they go back and do 11 and finally 12. So even though this is an arrow, stroke 8 comes a long time before stroke 12 actually appears, which means we can't count on people to be finishing one object before they start to draw another. And one of the interesting contrasts here is consider this as an analogy to speech understanding. One of the nice things about speech understanding is once you've said it, the signal is fixed. You can say it again, but you can't go back in time and change the sounds that you made. And yet here we've got a problem where the basic signal has to be reinterpreted because I've added some more information to it after the fact. Now, so how do people make sense of this? One way we do it is with context, understanding the kinds of things that are being drawn. Here's an example of low-level context use. This makes sense to you, of course. You know what that is. And that makes perfectly good sense to you, right? And is it very clear to you that this is a curve and that's a corner? Okay, well, I have bad news for you. Those are identical. Okay, so why is it that you decide that this is, of course, a nice round curve and that's a sharp, well, if not a sharp corner, that's at least a corner? The answer is context, of course. Where does this appear? This appears with some other curves. This appears with some other corners. So you're doing interpretation based not only on the stroke itself, but the context in which it appears. We've developed a relaxation-based approach that works to take account of the other kinds of figures that are in the scene and in the stroke to try and influence the local context, even at this very low level of deciding where the corners are. Here's a higher level context use. I go back to my family tree domain for a moment. We have a basic lexicon, of course, and then we've got a grammar. The grammar allows us to draw things like this. So I've got a man and a woman who are married, and they have 2 children. Okay, all of that's a legal expression in the grammar. In most states, this is an illegal expression in the grammar. So what the grammar tells us in part is what kinds of diagrams are not going to appear, or at the very least are going to be highly suspect as an interpretation. So when the system first sees this, it says, ah, that's a circle, that's probably a female. And now we've got a line added to that, so that's probably a female who is married to someone. Then I've got this, the next stroke, but let's see. The problem here is that this looks maybe like a pentagon or a rough hexagon, which doesn't show up anywhere in the vocabulary. So the system basically switches from a bottom-up to a top-down mode and says, look, I've got this, which is a female. I've got that, which is a married to. If you, the low-level guys, can reinterpret this as a rectangle instead of as a pentagon, then I can make a good high-level sense of it, which the system does. It says, well, that's close enough to being a rectangle that we can call it a rectangle. So now the leading hypothesis is that this is a female married to a male, and we're in pretty good shape at the moment. And then, of course, the next stroke comes along, and all of a sudden we have to start reinterpreting again to make sense of all of this as the user's drawing. But that will give you a rough sense of what I mean by using context to make sense of the drawing, even in spite of noise that's present. Now, I said to you earlier, we want to do descriptions of shapes and match those descriptions against the sketch, because it's much better to be able to have a description than have to write the code. The problem is that description matching is actually fairly slow. There's lots of different ways that, for instance, the symbol for that a ground symbol might be found in this diagram, because basically it's just 4 lines, a vertical line and 3 horizontal lines. Well, there's lots of possibilities here where that could be interpreted. So our task is to try and figure out where things might be in this drawing in a reasonably fast and efficient way. The idea we came up with, we actually borrowed from some work from Jitendra Malik on computer vision. The basic idea is called a shape context. This is a circular histogram, and it divides a space up into these bins. And the trivial idea is count the number of dots in each of the bins. Get the idea? Okay. That gives me a rough idea of the kind of shape that surrounds this particular point. So I'll take my target, my template, run this operator around a lot of it, and collect a whole collection of these filled-in histograms. Then I'll do the same thing with the sketch and try and say which points in the sketch have similar histograms to, let's say, this one here, which is centered on one of the dips in a resistor symbol. Okay? So I run these things over my templates, run them over the diagram, and then look for the places where the histograms in the sketch seem to match the histograms in the template. And, of course, a lot more interesting work goes on in trying to decide what similar means, how I aggregate these things together to decide that a lot of hits here that look like a resistor means that's a resistor and not something else, and so forth. But the basic idea is, as you can imagine, this is a fairly simple and quick operation, which gives us a quick, appearance-based approach toward initial segmentation and identification of the objects in this sketch. Okay, we've worked in a number of different domains. As you can see, we've talked about mechanical engineering. We did something in family trees. We've also taken a look at software design. A couple of years ago, we came up with a simple implementation of this idea. This is a sketch of a class hierarchy for an object-oriented program. We took our existing code and gave it the ability to recognize that set of symbols, including, by the way, the different kinds of arrows from UML, Universal Modeling Language. And then, as I said, our job is to recognize the sketch and hand off to a back-end program. In this case, the back-end program was Rational Rows. So we handed off the sketch interpretation to Rational Rows, whose job was then to generate, in this case, Java code corresponding to the sketch we've just drawn. The user's experience is doing something like this. I get to sketch the architecture of the program, and code for that class hierarchy comes out the other end. Now, this is an interesting and very intriguing kind of application. We really only scratched the surface of it. The interesting and hard problem is, well, this is a good kind of graphical notation for saying something about a program. What else can I describe about a program in graphical terms? How much of the code can I actually draw and then have something interpret? I mean, if you want to, we can go back to fundamentals like flowcharts. What other kinds of graphical notations are there for code? Our newest demo, it's a kind of pre-alpha state. I brought it with me above the objections of everybody who's working on it, but I'll have it for the demo fest for tomorrow, is actually circuit analysis. We've got a system that's capable of interpreting symbols like this. These are the cleaned up versions after the system has recognized it. It's a simple RC circuit, of course. And in this case, the thing we hand off to in the background is SPICE, which does an instantaneous simulation of the circuit so you can see its behavior. What we want to do with this is put it on a large screen touch-sensitive display in the classroom so the teaching assistant can be sketching a circuit, say to the students, what do you think the voltage behavior is? Have them answer, instantaneously say, no, look, see, it looks like this. And now let's try changing a few parameters, run it again, and have it a very natural sense of being able to sketch circuits and watch them behave essentially in real time. One other thing that's interesting about this demo, if I zoom in on a part that wasn't on that previous slide, see this symbol here for a voltage source? We're actually using that idea that I showed you earlier of having shape descriptions. In this case, let me just take a piece of it. We have this thing called the plus sign, whose name is P. We have something called the horizontal line, whose name is M. And by the way, this circle here contains the plus sign. It contains the minus sign. And the plus sign is supposed to be above the minus sign. So we've actually got an interface in which you can describe the structure of a symbol, and all of the recognition is running off of that description of the structure. So if you want to change it, it's very easy to change it, and then watch the thing recognize things differently. Okay, one final comment, hardware. We started off with electronic whiteboard kinds of things, switched to tablet computers when they came along, and they're a very interesting and powerful kind of environment. But we still have a hankering to go back to this. Wouldn't it be nice to have a digital drafting table, a digital design environment, something that felt as big and natural as a drafting table, and yet you could draw on it? So we're looking at various ways to make that possible. One of the things we're looking at is one of these large-scale 42-inch touch-sensitive displays, which we could mount horizontally or almost horizontally and have somebody be able to draw on and have it feel like a digital desktop. The basic idea here is we're thinking about reinventing desktop computing. You see, your desktop should compute. Why not? It's just sitting there holding up coffee cups otherwise. Why isn't it a drawing-sensitive, gesture-understanding, speech-understanding surface? Wouldn't that be nice? Okay, let me summarize. Once you understand the sketch, once we turn pixels into descriptions of objects, lots of things are possible. We're agnostic about the back-end program that we can connect to. We're happy to connect to lots of things. Lots of people say the job of interface designers is to create good interfaces. Let me take a slightly radical position and to say the way to break down the barriers between us and software is to think about eliminating interfaces. People don't have interfaces. You just kind of go up and talk to them, okay, and interact with them. Wouldn't it be nice if software didn't have interfaces either? It felt as natural as interacting with another human being. And we think that that natural interaction is crucially enabled by intelligence. We need programs that are smart. We need them to understand about sketching, about gesturing and speech. We need them to understand about the domain, be it physics or circuits or UML diagrams. And we need to understand about the task, the design task itself. So we think that if we put all of this stuff together, we enable an interesting and powerful kind of interaction that we hope eventually feels as natural as walking up to a whiteboard, talking, gesturing, and drawing. Thank you. I guess I can pause for questions if we have any. Yeah.
A couple of clarifications and a challenge. James
I'll take the questions.
Okay. James Landay's earlier system, Silk and Denim, attempted to do a lot of these things. You've taken some new application domains, but could you clarify the distinctions?
Yeah, the distinction is James's system explicitly did not attempt to do a lot of these things. One of the interesting things about James's work, and I know his work well, he and I have organized a couple of sketch understanding workshops, is that he's looking for lightweight tools that make it easy to do conceptual design and explicitly shied away from doing recognition. A key thing here is we are trying to understand the ink that's there in a fairly basic way.
Well, he's doing recognition of the shapes of rectangles and lines connecting to make node link diagrams. And all that. Early geometric kind of recognition, and we're trying to push it into much more interesting things than that. I'd be interested to see more. Okay, I think you can elevate your, to be as good as paper seems to be a very low bound. I think you ought to be far better than paper, and I think you're on your way to some of those things in terms of the capacity of these tools to be able to do things. Once you put it on the screen, you can size it, change it, flip it, do much more than you could ever do with paper.
Yeah, that's why it's called magic paper.
Yeah, okay.
The whole idea, remember, what I said was the idea was to make the interaction as natural and easy as paper, but make it much smarter than that.
Well, I think more potent, and so I think
yes, potent, smart.
Okay.
Yeah.
I do. The other challenge was about speech being integrated. The work in multimodal interfaces have sort of abandoned that, and that the interaction of doing speech and gesture at the same time does not seem to be proved beneficial. That the task switching modes have failed, as it did in aircraft pilot.
Switching modes.
Task switching when you when you do dual task, when you do speech and pointing, as was tried very much for 25 years in aircraft, in pilot situation by the Air Force, and so the movement was away from that in recent years. And I'm wondering why you still think there's a hope.
Because I'll tell you, and hope is a good term because I have no proof of this, but my belief is that the key is to make it what people would naturally say. That to the extent that you invent languages, and some number of people who are working in this multimodal stuff have essentially turned the speech into I shouldn't say turn. They use speech as a command language. And the question is, if you could really go up and talk to the blackboard, what would you say? And if you could do that and the blackboard could understand it, would that work better? I don't know. But I think it's worth a shot.
I think people have tried.
We'll see.
All right. Good luck.
I think there's people who have found that speech and gesture often simplifies. For example, Sharon Oviatt, I hope I'm not misphrasing her, but she's done some studies that have shown that when you can do gesture or speech, it often simplifies what people say.
It's just her work on citing and her disfluencies in the combination of the vowels. So the later work separates out that either you use gesture or you use speech. But the integration of them seems to produce slower performance and higher error rate.
You also have to worry about the kind of sites. Talk to some of the people involved in them, and they will not use a speech-based interface. Because if you talk to the same military people and say, "Hey, I have this interface, it does sketch understanding," and they say, first question they ask is, "Does it use speech?" And if you say, "Yes, it requires speech," they'll say, "No, I won't touch it."
Why?
Because the speech stuff is too noisy. If you're being shot at, your voice changes. And so, there's all these problems with speech.
Cognitive load of speech is much greater than you usually estimate. That it is more difficult to be solving problems at the same time as generating speech.
And Randy, to your point about naturalness, that's exactly right. command languages don't work.
Right.
So we kitted up a general once. He puts on the headset and says, "Okay, computer, we're going to do a frontal assault down the." And no, general, you got to do this. You got to do this.
Yeah, right. That doesn't work. Right. Which is why I think if we could get to the stage where the system could handle, okay, we're going to do a frontal assault. No, that way, no further left. Instead of full grammatical sentences and commands, we might have a shot at it. But I agree. It's an open question. We'll see. Yes, sir.
I just need to know if Magic Paper is available for other people to use in class.
We have, there's the, there's the physics simulator that you're calling it? Physics Illustrator, right. Yes, there is a version.
It's available for download from iCampus.
Okay. Thank you. Kimberly.